Okay, welcome to another video. This video we'll be looking at the branch and bound algorithm. So we've met integer and binary variables for our linear programs. How do we actually solve a linear program with integer and binary variables? Sometimes we just get lucky. We could try the simplex method and it might be that the solution that we get out satisfies our integer and binary restrictions on those variables. Some specific types of problems actually have this structure, such as transportation problems. As long as the parameters are integers, then the solution will be integers. And so that's a really cool property of those types of problems. But in general, most problems don't have that property. And so we need to come up with a clever way. And that's kind of the branch and bound algorithm. I will say kind of the naive approach might be, well, if I have integer and binary variables, and if my feasible region is bounded, then I actually have a finite number of potential solutions, and I could just check them all. However, finite doesn't necessarily mean small. And problems, especially integer and binary problems, can grow really fast in the number of possible solutions as you add more variables. And so adding more variables can drastically increase the size of a problem. If you have a problem with 10 binary variables and no other constraints, that's 2 raised to the 10th power number of possible solutions. And 2 to the 10th is right around 1,000. So that's pretty big. If you have 100 variables, then it's 2 to the 100th. And that is then 1,000 to the 10th power, which is 10 to the 30th power, and that gets really big. Okay, and so 10 variables, not too much of a problem. 100 variables, you're thinking something that's going to run for 30 minutes to an hour on a typical desktop computer. 1,000 variables, you're not going to see the end of that in your lifetime, and if you have to kind of manually check all the different possibilities. Um, so listing them out, kind of naive approach isn't going to work. But if we're clever, we don't have to check all the possibilities, because some of the possibilities we know pretty quickly won't be interesting. Okay, and that's the idea behind the branch and bound. We can eliminate whole regions from consideration if we've already found a better integer solution and we know how good the solutions in that region could be. And so to get an idea of how good those solutions in the region can be, we relax our problem and try to get an upper bound on how good the solutions can be. Okay. So for this problem and for branch and bound, it works better to work through an example to understand what's going on. And then we'll review sort of the steps rather than me talking through the steps and then doing an example. So let's start off with an example. Here's our kind of 2 variable linear program with integer variables. And so we've got 3 constraints here, really only 1 functional constraint, and the other 2 are bounds on the variables. Let's actually look what the feasible region of this problem looks like in Desmos. So here it is. Here's maybe a little trick that I figured out as I was experimenting with this, is if you want to have sort of compound inequalities, you put them in curly braces with a :1, comma 0, and then you kind of just string them all together there. And then at the very end, you put greater than or equal to 0, and that will give you your kind of shape of compound inequalities. Okay, so this is our feasible region. Here's that functional constraint here. This line here is the upper bound on x2. Here's the upper bound on x1. And of course, we've got our non-negativity constraints kind of keeping us here in the first quadrant. Okay, so that's our feasible region that we're dealing with. Let's go ahead and talk about a little bit about our strategy. So back to our problem. The first step in branch and bound is to relax your problem. Okay, that sounds nice. But what does it mean to relax our problem? In math speak, a relaxation is a different and hopefully easier problem that gives an upper bound on our original solution, at least for a maximization problem. Lower bound for minimization. Essentially, it tells us what is the best we could hope for our solution, for our objective value. Okay, there's a couple different possible relaxations. Really, we could get rid of any of the constraints, and that would be a relaxation. But the most useful constraint to get rid of is that integer requirement. And so probably the most common relaxation is to relax the integer requirement and treat all of our variables as continuous variables. Okay, that will, yeah. Treating them as continuous variables enlarges our feasible region from just being at the nodes of the integer values to sort of being a whole region. And so when we get a solution to the relaxed problem, it's always going to be better, as good or better than the integer solution in that region. Okay. So we're going to call this relaxed problem node 0. And our first step is to solve that relaxed problem using the simplex method. If we happen to get an integer solution, then we're done, right? Some problems have that nice structure where that will happen right away. But chances are we won't get an integer solution. And so then there'll be a step 3 coming up. But let's go ahead and do step 2, solve that relaxed problem. Here's that problem in OMPR. We've got the two variables. They have lower and upper bounds both. And we really just have here's the objective and then one functional constraint. We solve that out. And here we get our optimal solution, 8, 2.25. And the optimal objective value is there. Notice this is not an integer solution because the x2 variable has a decimal part to it. And we get status equals success there. Jumping back to our picture, this point here, 8, 2.25, that's going to be, let's see, can we get the node on there? Okay, well, anyways, that's going to be this point right here in the diagram with an x1 value of 8 and x2 value of 2.25. And so that turns out to be the optimal corner point when we ignore the integer restrictions. Okay, it's not an integer solution though, so now we need to move on to step 3, which is to branch. Okay, so when we branch, we take one of our non-integer variables in our previous solution. So in this case, 8 is an integer, 2.25 is not an integer. So we're going to branch on x2. If we had more non-integer variables, we could choose any of them to branch on. So we're going to branch on x2 equals 2.25. And what we do is we take our 2.25, we round it down, and we get one problem where x has to be less than or equal to the rounded down value. And then we get another problem where we add on the constraint x2 has to be greater than or equal to the rounded up value. So we take 2.25, we round it down, we round it up. We make one problem with the less than the rounded down value and one problem with greater than the rounded up value. And so our node 1 here will add on the less than or equal to constraint here. Our node 1b will add the greater than or equal to constraint here. Okay, let's look at what those look like visually. Okay, in Desmos, x2 is y, and so I'll go ahead and copy this twice. And then let's see, we'll move one of them here down below node 1a and one below node 1b. I'm going to go ahead and turn this off. For node 1a, I'm going to add that our x2 variable, which I'm calling y for Desmos' sake, is less than or equal to 2. And then I do :1, 0. Okay, and that gives me sort of this rectangle down here. And node 2a, I'm going to take my x2 value of 2.25 rounded up and say that y needs to be greater than or equal to 3, colon 1 comma 0. Okay, and that gives me this region up here. And so kind of turning back the original one on, when we branch, we essentially take out a strip. Notice that this strip doesn't include any integer solutions, okay? We've essentially only taken out the sort of non-integer values of x2 between 2 and 3. So we've included, like right along this line, there's a bunch of integer solutions here, 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 and here. And then along this line, there's some integer solutions there. But we've taken out the non-integer values in between them. Okay, and that's the big idea behind branching. We haven't lost any integer solutions when we branch and kind of take out that strip, but we've now split our region into two regions that still contain all the integer solutions from before. Okay, so this is node 1A down here, and this is node 1B up here. Okay, let's go back to R, and let's actually solve each of these separate problems on their respective domains. So we've changed the feasible region, objective stays the same. So solving node 1A, we get an optimal solution of 8, 2, and an objective value of 34. Node 1A is our first and currently our best, it's our only integer solution with an objective value of 34. And so we're going to call Z star our current best objective value. That's going to be 34. Visually, that's this point right here. Okay, and it has an objective value of 34. It was pretty close to the corner point that we had before that was right here. We're now just down a little bit. And you think, actually, that's maybe the solution that I would have gone for if I were just rounding my solution. And so doesn't always happen that you end up at a solution that you would have rounded to, but it does in this case. For node 1B, with the greater than 3 constraint for x2, we get 6.5 and 3. Notice that the only thing that I'm having to change is a lower bound here and an upper bound here. And the nice thing about OMPR is that we can take a previous model, so node 0 model, and kind of just add to it, and we can get a new model with just the updated parts of it. So node 0 contains all the objective and constraints and variables from before. Okay, back to node 1B. We get a non-integer solution with x1 equals 6.5, x2 equals 3, and an objective value of 34.5. Okay, 30.4.5 is better than our current best, so there's still potential that we might find another solution within node 1B's region that is as good or better than what we had in node 1A. Okay, so we continue moving with this region. Let's look at where that is. So that point would be this corner right here, where we get x is equal to 3 and x2 is equal to 3, x1 is equal to 6.5. Okay, so that's that point there. So step 5 in the process is then to evaluate the nodes and branch again if necessary. So node 1A is an integer solution. It's going to be the best integer solution in that region for node 1A, and so we don't need to branch any farther off of node 1A. So if you hit an integer solution, you stop and kind of either it's going to be your current best or it's going to be worse than something you already have, in which case you also stop. On the other hand, node 1B did not give an integer solution, but its upper bound is better than our current best, and so we continue. Okay, and we'll go ahead and split again on node 1B. This time splitting on x1, which is the non-integer variable, and we'll split into node 2A and node 2B by rounding 6.5 down and rounding 6.5 up. And so node 1A will be x1 less than or equal to 6, and node 2B will be x1 greater than or equal to 7. So let's actually go ahead and add node 2A and 2B to our Desmos graph here. And so here I'll add a note. oops, I had this one wrong. This was node 1B. Now we're going to have node 2A. And I'll add another note for node 2B. Okay, node 2A and node 2B are going to branch off of node 1A. And so I'll kind of go up here and I'll take node 1B. Oh, I think I keep saying these nodes wrong. Node 1B, they're going to split off node 1B. So I'm going to duplicate that twice and grab one here and put another one down here. Okay, so node 2A, I'm going to do x1, which is the x variable in Desmos, and x is less than or equal to 6. Okay, and then node 2B, and then node 2B, I'm going to do x greater than or equal to 7. Okay. It might help to turn off some of the other ones, so I'll go ahead and do that. And so node 2A is this one here, where x1 is less than or equal to 6. So comparing that to node 1B, we cut off just the corner triangle right at this tip. Okay. On the other hand, node 2B is the part where it's greater than or equal to 7. Look at this picture though. The line x equals 7 is right over here. None of that is to the right of that. And so node 2B is invisible. And maybe that's something to think about, and it'll show up when we then go to try to solve it. Okay. So let's jump back into the R output here. Node 2A, we go ahead and solve it. It's then going to give us an optimal solution of x1 is 6 and x2 is 3.25. So looking at node 2A, let's turn off node 1B. So we're going to get x1 equals 6, x2 equals 3.25, and so it's this little upper corner right here. And that's going to be a non-integer solution with an objective value of 34.25, still better than our current best. Node 2B, when we go ahead and try to solve it out, notice it gives us a solution, but when we check the status, it says error. Okay, that error is because node 2B does not actually have any feasible solutions. Interestingly, OMPR will give you sort of the closest solution to being feasible. So that's actually kind of interesting. It gives you 7.3 that satisfies some of the constraints, but not all the constraints. In that if you plug 7.3 back into the original functional constraint, it'll violate that. So it does its best to get as close as possible, but it'll also give you the error here. And so be wary that not every time that OMPR gives you back a solution is that solution actually feasible. You should always be checking that status. Okay, so node 2B has no feasible solutions. It's the reason why we sort of saw an empty feasible region when we looked at node 2B. Okay, so now we're back to step 5 again, evaluate the nodes and branch. For nodes that have no feasible solutions, they're essentially dead. We're not going to branch on them. Node 2A, on the other hand, has a non-integer solution that's better than the current best, and so we'll branch again on node 2A. Node 2A, it was x2, which was 3.25, and so we're going to branch on x2. And so we're going to round 3.25 down to 3 and up to 4 to get nodes 3A and 3B. So I'm going to turn off node 2B because it's not interesting. Let's go ahead and add notes. So this will then be node 3A. And then I can add another note for node 3B. And we're going to take node 2A and duplicate that. So node 2A, duplicate it twice. And I'll grab those and bring one under 3A and one under 3B. Okay, and we're splitting on the second variable, which is our y variable in Desmos, and it's going to be y less than or equal to 3. For 3A, and it's going to be y greater than or equal to 4 for node 3B. So, node 3A, I was worried this might happen. It's ending up invisible. I will say it ends up being actually just a line here. Because looking at it, we have this constraint that it's greater than or equal to 3 and it's less than or equal to 3. So it ends up being exactly y equals 3. Okay. And so it's not actually infeasible in this case, which is maybe a drawback of using Desmos. I wasn't sure how well that would show up, but yeah, so yeah, it's going to be the line y equals 3 and x is less than or equal to 6. Okay, node 3B is going to be this region up here. So let's look at the output from this third generation of nodes. For less than or equal to 3, we solve it out. We get a solution 6, 3, and a status is success. So it actually is a feasible solution. And it gives us an objective value of 33. Okay, it's an integer solution, so we're happy. But it's worse than our current best. And so we're not going to keep this as our best node because we've already got a better integer solution. Node 3B, we split it and we get a non-integer solution 4.5 and 4, and that has a objective value of 33.5. Also now worse than our current best integer solution. Okay, and so now when we evaluate our nodes, we have a integer solution that's worse than our current best, so we stop on that. We have a non-integer solution that's worse than our current best, and so we stop on that. Okay, this is called fathoming a branch. I'm not 100% sure why or kind of where that notation comes from in the literature. But yeah, anytime we're at a branch and it's worse than our current best, we know that we don't have to continue on that branch because we won't find anything better than, for example, in node 3B, nothing will be better than 33.5, and 33.5 is worse than 34, and we have a solution that's an integer solution that's 34, and so we can stop looking down node 3B. No need to go further branching there. Okay. So let's kind of wrap this up. The optimal solution in this case is 8.2, which was, I think, node 1A. And that had an objective value of 34, and that is our overall best. Okay, it was our current best, and we could have eventually found something that was better than it. But in this case, the first best was our overall best. And that's maybe not uncommon to see in practice. Okay. So an overview of what's going on here is we're branching kind of for branch and bound, the steps are relax the problem, solve the relaxed problem, branch on any non-integer solutions, solve the nodes of the kind of resulting problems that you get from branching, and then evaluate the nodes and branch again if necessary. Okay, and then you sort of repeat steps 4 and 5 over and over until all of your nodes have terminated. Okay, and so there's 3 ways we can terminate at a node. One is we can find an integer solution. Okay, if it is better than our current best, it becomes our new current best, and we store it and we update our Z star. Otherwise, if it's worse than our current best, we throw it away. Another way we can terminate at a node is we find no feasible solutions to the relaxed LP. There's nothing to work with, so no need to keep going. And so we sort of throw that branch away. And the third possible way we can terminate is we get to a non-integer solution that's worse than our current best Z star. And then we know that going further down that branch isn't going to get any better. And so we stop on those branches as well. So one of these three things will always sort of terminate a branch. Okay. So I've been saying this words of branch quite a bit. It's maybe good to kind of actually draw a diagram of what we are talking about when we're saying branch and bound. And so let's actually jump over to the doc cam and I'll kind of sketch out what's going on here in the branch and bound. Okay, let's talk through this sort of branching diagram, which is kind of conceptually what's going on as we're using the branch and bound. And so we start off at node 0, which is our relaxed problem of our original problem. So we've relaxed the integer constraints. And we get this solution with a non-integer variable, and we get an upper bound of 35.25. And then we split on the non-integer variable x2, and we get node 1a and 1b. 1a ends up being an integer solution. That's the current best. And so you'd sort of store this solution at this point and kind of make a note that z star equals 34. Okay. And then that's going to be what we compare everything else to. So now looking at this, that's better than 34. And so we kind of keep going on this node and we split on the non-integer variable here, rounding down to 6 and rounding up to 7. And that gives us nodes 2a and 2b. Node 2b had no feasible solutions, and so it sort of dies off. We don't branch any further there. Node 2a is still better than our current best. And it's a non-integer solution, and so we split again. This time on x2, rounding down to 3 and rounding up to 4. That will then give us 2 more solutions, but now notice that the upper bounds for both of these solutions, which this one's an integer solution, but they're both now worse than 34. And so these ones we'd both label as fathomed. Okay. And so all of our terminal nodes end up either as no feasible solutions, fathomed, or kind of our current best. And what I will say is if you go on and if this integer solution had been better than this one, even though it's kind of going to be impossible to get an integer solution that's better than that coming out of here. But if it had, then we would have fathomed this one and continued on, and updated this one to be the current best. Okay. Nice thing is that branch and bound will sort of find all optimal solutions that are have the same objective value, as long as you kind of store them and keep branching on them. And so it would have been possible that we got a z equal 34 here if things had sort of lined up just right, and then we would have had 2 optimal solutions with the same objective value. Okay, so that's sort of an overview kind of with a branching diagram of what's going on underneath the hood in the branch and bound algorithm. Notice that we solved 1, 2, 3, 4, 5, 6, 7 linear programs along the way. And so you can kind of see how introducing integer variables balloons the amount of work that needs to be done. I will say most implementations of mixed integer linear programs are smart about the fact that each successive linear program is related to the one before it, and so it doesn't have to start from scratch. It will start from the previous solution. And yeah, think through what we did in sensitivity analysis. If we add a constraint and our previous solution is no longer feasible, then we'd pick up with the dual simplex method to continue from there. And so that's what's going on underneath the hood as they're doing the branch and bound algorithm. So that wraps up this video. I'll have another video with another example.